The emphasis today from our speakers will be, of course, on GPS and on Galileo, but I'd like to spend a couple of minutes just to point out that there are several other systems being developed. I'm sure many of you know about them or even work on them that I'd like to mention, and a couple of our speakers will say a little bit along those lines as they give their prepared talks. So let me mention the four other systems. The first is GLONASS. The GLONASS system, the Russian GLONASS system, of course, originated in the 80s and under the old Soviet Union. And when the Soviet Union dissolved, the GLONASS system went into disarray for quite a number of years. In fact, I think it fell to a low of 7 satellites in 2001. But now there's a resurgence of interest and funding and so forth for that system. And the constellation is once again being replenished. There's 24 satellites now, including 3 that were launched in a single launch earlier in September. There's a Chinese system, the Chinese Compass system, which is being developed to consist of 5 geosynchronous satellites, 3 inclined geostationary satellites, and then 27 satellites in MEO, or medium orbit, such as the current GPS inclination, GPS orbits. And the Chinese have launched 4 satellites. The system is to provide positioning to 10-meter accuracy for all users, and then better than that for authorized users. And it's going to and is transmitting on multiple frequencies in or near the GPS and Galileo frequency bands. The fourth is an interesting one, not that they're not all interesting, but this one is particularly interesting, the Japanese system, the quasi-zenith satellite system. Japan, as everyone knows, is an extremely developed technologically country, but has a lot of tall buildings in urban areas. And so a satellite system that needs to get a signal to the ground in urban canyons, the existing systems suffer from attenuation and reflections and so forth from the buildings. And so Japan is launching a system called as I said, the QZSS, the quasi-zenith satellite system, into orbits that are inclined 45 degrees into near geostationary orbits, geosynchronous orbits rather, that are inclined 45 degrees so that they can be seen at high elevation angles in Japan. So the first of 3 of those was launched this past September 11th. As I mentioned, 24-hour, slightly elliptic 45-degree orbit. And then the fourth one is the Indian Regional Navigation Satellite System. The government of India is also developing its own independent system known as IRNSS, as I just mentioned. The constellation to be completed in 2014 will consist of 7 satellites with an orbital geometry that assures at least 4 of them are always in view over the Indian subcontinent. So this is a specific system aimed for that particular geographical area. So those are the 4 systems. They'll be mentioned to some extent in some of the presentations, but will not be emphasized as much as GPS and Galileo are. So I thought I'd mention them to start with for you. So I'd like to introduce our participants, and I think what we'll do is let me just introduce all of them to start with, and then they can come up individually and give their presentations, and then we can have questions as you see fit. So the first speaker will be Dr. Bradford Parkinson. He is the Edward C. Wells Professor of Aeronautics and Astronautics at Stanford University. His involvement in GPS goes back a long time into the early 1970s. When he was a colonel in the Air Force in the United States, actually. And I'd say he's the person who's most responsible for synthesizing elements of various competing navigation systems into a single viable system. And he led the U.S. Air Force Program Office at that time that laid the groundwork for the system that we now know as GPS. And I'd just like to make a little commercial for you this evening at 6:30. Dr. Parkinson will also provide a highlight lecture, so we'll have an hour to tell you about the history and prospects from his perspective of GPS and other space-based navigation, navigation, positioning, and timing systems. Then we have Mr. Didier Fevre. He's the head of the navigation department for the European Space Agency. Prior to that, he spent 17 years at CNES, the French Space Agency, where he has experience in both programmatic and operational areas, including he served as deputy director for programs, and he joined ESA in 2000 and served in his current position since 2005. The third speaker is Anthony Rousseau. Tony Rousseau is the director of the U.S. National Coordination Office for Space-Based Position, Navigation, and Timing, a role that he has had since early this year, and he was telling me that this isn't really associated with any particular piece of the U.S. government. He works for 10 agencies, so he has a lot of different bosses that he has to deal with. His experiences in policy and development, requirements definition, planning, and budgeting for space-based systems. And the fourth, but certainly not the least, of our speakers this afternoon is Mr. Barry Smutny. He's the Chief Executive Officer and President of OHB Systems AG in Bremen, a position he's held since early last year. His technical background is in optical communications, laser comm. I don't know if he's going to talk about that today or not, but he does have an extensive background in that area. Prior to his present position, he was, since 2003, the CEO and president of TSAT Spacecom. So those are the four speakers. I won't get up again, I don't think, between them, and so we can ask Brad Parkinson to come up first.
Thank you, Joe. This afternoon, I'd like to make a few remarks about moving ahead with the global positioning and timing service as opposed to GPS. Emphasis here is on service, and in particular, I'd like to focus on three issues that I will shortly describe. All the users should be very happy. Great news. We have many new satellite systems and signals on the way. They should enable improved accuracy, availability, integrity, continuity. We already have hundreds of applications, and no doubt this is going to lead to even more and greater capability in the applications we already have. Some of the opportunities as far as satellite systems are concerned, in GPS we have the only current operational civil signal. The next generation is going to have 4 new signals at 2 new frequencies. GLONASS is coming along with the next generation. They have promised that they are going to have a signal similar in type to the one used by GPS. Galileo, of course, is the next generation with 4 new civil signals at 2 new frequencies. COMPASS by the Chinese, and QZSS, and there are a number of other augmentations. With all those systems, we also have a certain amount of coherence in the signals that they're going to be offering. This shows a diagram of the frequency spectrum, and if you concentrate on the bar on the right, the so-called L1 band, you'll see that most of the new satellite systems will be broadcasting in that same band, simplifying a receiver and its design. Hopefully there will be a single coordinated L1C signal that's going to be used in that band for international applications. L1CA by GPS is the only fully operational civil signal. So, an important question. We are victims of our success. GPS has enormous capability. It's led to worldwide dependency. So what do we do to ensure that that trust is not misplaced? Well, the first issue that I foresee is that of availability. It sounds like great opportunities coming ahead, but it turns out GPS has many old satellites. 2F is quite late. 3A is ahead of schedule, but the first launches are not until 2014 and 2015. Galileo is delayed. There are cost challenges. GLONASS is delayed. They're working in a longevity problem that makes it very difficult to keep the full 24 populated. COMPASS is moving ahead, but the details are not clear. In a little more detail, as far as GPS is concerned, I think the issue number 1 is sustainment, ensuring that the constellation is available. The average GPS on-orbit life is 9.4 years. One of the satellites is almost 20 years. The first 2F was launched in May of this year, but when do we see the next 11? The first GPS-3 is currently available for operation in August of 2015. When will Galileo be certifiable? Will GLONASS or COMPASS be completely available to the civil community throughout the world? it's imperative that we avoid what we call brownouts, a diminution of the number of satellites that we currently have on orbit. And to that end, I believe the answer to sustainment is sustained high-level support for earliest GPS 3 delivery, as well as the continued funding and support for the development of Galileo, as well as the continued modernization and fielding of GLONASS. I'm a big fan of all of these systems, in spite of the fact that I'm normally just identified with GPS. Let me turn to the second issue very quickly. Is the interference problem significant? This is a press release that says a U.S. federal court validated the police's right to attach GPS tracking devices to vehicles. Well, there is a response from a company called China Vision, or Vision actually, and many other companies, a handheld GPS jammer whose cost is only $33, and you plug it into a cigarette lighter. So what do we do about this? There are many examples of what I just shown you. We can increase the power slightly. Increasing satellite power is a very hard problem. We can use local transmitters. They don't have the coverage you probably need. The receivers can be modified. We can have beams that actually point at each of the satellites. We can increase the averaging time or processing gain. We can integrate it with inertials to coast through areas where we have interference. We can integrate with chip-scale atomic clocks. And with all the satellite systems, we will also have signal or frequency diversity, so interference on a single frequency can be avoided. We can also put all those channels into what we call a vector receiver that has a single filter for the whole ensemble of perhaps 30 satellites. There's a backup solution to GPS that was highly recommended at the national level in the United States. ELORAN, the response by the bureaucrats, was to turn off the money and promptly tear the towers down. This is a typical irrational experience or response, in my opinion. My colleague, who is under greater constraints than I, can't say that, but I, being a university professor, get to say things like that. And of course, there's regulation. The Department of Homeland Security and FCC need a more active program to detect interference, shut it down, prosecute deliberate interference, and stop the internet sales of jammers. So issue number 2, robustness, and the answers are to get affordable receiver interference rejection technology, and perhaps the backup of ELORAN or something equally capable. The last issue I'd like to touch on is we have a new ensemble of global navigation systems. Will they cooperate or will they compete? And there are many levels of cooperation. I call these degrees of getting along. The first is compatible. That says, I won't hurt you, you don't hurt me. Interoperable. I'll try yours, you can try mine. And the third, which I think is the real solution for the global users, is interchangeable. So that any 4 satellites, you recall GPS requires 4 satellites to navigate normally, any 4 satellites will do. And so issue number 3 is, can we attain total interoperability? I should hasten to say that many groups are working very hard on this. The real measure, interchangeability, mix and match with the same accuracies. The prerequisites, I think, is the new civil signal, an international signal that's going in at L1, to have seamless augmentations such as WAS and EGNOS, to have true synchronization of clocks in a common grid, and the payoff is availability, accuracy, and of course robustness for the worldwide users. If you want to attain interchangeability, the simplest is a common clock and geodetic system, but national pride would get in the way. So there is a new proposal that I'm not going to elaborate on called cross-augmentation reference systems, in which each individual satellite broadcasts the correction to use that satellite in the other constellation. And in so doing, it becomes truly interchangeable. So the earlier question that I raised, what must we do to ensure that the trust in our global positioning and timing service is not misplaced. We should address those, in my opinion, we should address those three issues: sustainment, robustness, and interchangeability. Thank you.
Good afternoon, and thank you for having invited ESA at this plenary session. So, with the GNSS infrastructures today, we know at any point in time, at any place in the world where we are. I will try in 10 minutes to tell you where Galileo is today. Let's start with a short reminder. In 2009, Mr. Tajani, at this time European Commission Vice President for Transport, is now Vice President for Enterprise and still in charge of the Galileo and EGNOS program, announced the official start of operation for EGNOS. So the open service was officially opened. This is the first step for Europe to enter into the club of the global navigation service providers. Then, in summer this year, the French National Civil Aviation Authorities have certified the operator, and the safety of life service of EGNOS will be formally open this year. Performance in terms of coverage and continuity is shown on this slide. You know that today Galileo covers the western part of Europe mainly, and has achieved a very continuous signal since 2008. More important maybe, and it's important in this plenary international session, is to show that today the SBAS systems, we have 3 systems operational in the US, in Europe, and in Japan, and you see on this slide the coverage. It's already a first service offered to major regions in the world. But if we now prepare a dual frequency, dual GNSS, at least dual, with a limited number of additional stations, the SBAS system could provide to the world a service of high quality. And I think, to go in the direction indicated by the previous speaker, that is probably the first priority for expanding and fostering international cooperation. Oops. Let's start now with Galileo. In 2010, beginning of this year, the first 3 contracts for Galileo, full operational capability, were signed for the launchers, the system task, and the first satellites. This is a real start of the full capability of Galileo, which should take place soon. You see on this slide the architecture of Galileo, which is a usual one. The users and service providers are not part of the infrastructure delegated to ESA, so I will mainly focus on the satellites. We have 30 MEO satellites providing the various signals of the Galileo navigation. Those satellites are monitored by a set of sensor stations distributed all around the world, connected to 3 control centers in Europe, and the control centers are linked to the satellites through a network of uplink and TT&C. And ESA is today procuring the full infrastructure. In terms of overall schedule, we started with the first satellite in orbit in 2005-2008 with a testbed satellite. Now IOV, which is the in-orbit validation phase, is nearing completion, and we expect to have the full constellation in place around 2016, with the first step, an important step, in 2014, where we'll be able to provide the first services. GOV-A is the first test satellite launched by ESA in 2005. Still operational, so far beyond the expected lifetime of the mission. We have decided to extend the mission. This satellite is very useful to characterize the orbital environment and the characterization in space of the atomic clock, which is a rubidium clock for this satellite. GOV-B launched in 2008. is still operational. This satellite has a payload which is very close, representative of the IOV payload, in particular with the signal generator and with the passive hydrogen maser, which flies correctly in orbit since the launch. Let's go now to the IOV satellites. We developed within the IOV in-orbit validation phase 4 satellites. You see on this slide the payload integration, which is well advanced at IADS Astrium in UK. The satellites themselves, the 4 satellites, are in the integration phase in the premises of Thales Alenia, Italy. And the integration is okay for launch in summer next year. As you know, Galileo, IOV, and FOC have selected Soyuz from Kourou as the primary launcher, and you see on this slide the status of the launch pad in Kourou. The launcher, we have already 2 Soyuz launchers in Kourou, and the tests are taking place now for a first launch which should take place in spring next year. In principle, Galileo is number 2 in the sequence of launches. Galileo uses a specific upper stage of Soyuz, and all the facilities for the integration of this frigate upper stage are already available in Kourou in the launch pad. That's for the satellite and the launcher infrastructure. For the ground station, which is probably the most complex task in terms of logistics and organization, the Galileo ground segment is distributed worldwide. You see on this slide a subset of stations, mainly on European territories, and also stations are already ready for the IOV launch. When we will enter into the full operation constellation phase, an additional set of stations will be needed, and the program has already selected additional sites, you see, again in European territories. It may be necessary to expand it to non-European territories. Beyond this sensor station distributed worldwide, ESA will use a specific site for in-orbit test system, and you see here the antenna recently inaugurated in Redut, Belgium, in the ESA center. The telemetry and telecommand site, we have 2 sites, one in the far north of Sweden in Kiruna, and the site is ready now for the launch. The second site is in Kourou for the TTNC, and Kourou is a major site for the Galileo program. Kourou hosts not only a TTC, but also a uplink station and a sensor station, plus, of course, the launch pad. The program is today structured around 2 ground control centers. The first one is located in the DLR premises in Oberpfaffenhofen in Germany. For the IOV phase, this site in Oberpfaffenhofen will be devoted to the control of the constellation, and it will be complemented to host the ground mission part later on for the FOC. The second center is located in Fucino, in Telespazio premises in Italy. This center is devoted first to the mission part of the ground segment, and will be complemented to host soon and later the control of the constellation, which will allow 2 centers to be fully redundant in a hot backup mode for the operational phase. So a number of remote sites has been deployed all around the world, from Kourou on the equator to Svalbard in the far Arctic place in Norway, from Papeete in Tahiti to Troll, an Antarctic station under the responsibility of Norway, and all the sites, around almost 10 around the world, are now ready for the launch. So let's go now to the FOC. Mr. Smouty will present the status of the satellites. As you know, the Commission acts as program manager and has delegated to ESA the role of system prime and the procurement agent, which means that ESA has to organize the procurement of the various elements of the infrastructure. At this date, 3 major contracts have been signed, the green ones on the slide, related to system tasks, space segment, and launchers. 3 major work packages are still to be contracted soon. As far as operations is concerned, the contract is ready, and we expect the signature of this operation contract with a consortium based mainly on DLR and Telespazio very soon, in a couple of weeks. For the ground segment, the ground mission on one side and the ground control segment on the other side, we expect to contract the final contracts to industry beginning of next year. Those contracts are based on the full operational capability and should, in order that Galileo delivers the full services around 2016. But it has been decided to have a staggered approach, and as soon as 2014, with a limited infrastructure, mainly based on 18 satellites and a limited ground segment configuration, the program should be able to deliver 3 major services: the open service, as said, fully interoperable with GPS, with limited performances, public regulated service, and search and rescue service, because you know that each Galileo satellite embarks a search and rescue transponder, which is fully compatible with the COSPAS-SARSAT network. One word on the space segment, and Mr. Smutny will come back. The selection process has selected 2 contractors, IADS Astrium and OHB, and the first work order related to 14 satellites has been awarded to OHB. So satellites are supposed now to be launched starting end of 2012 till mid-2014. Together with the contract of the satellite, the program has awarded a contract to Arianespace for today 5 Soyuz launches, so we can launch already 10 satellites with a firm fixed contract. For the 4 remaining satellites of the World 1, a trade-off is today organized. We have to make a choice between 2 additional Soyuz, which is fully compatible with the program, or with 1 Ariane 5, and a recent study has demonstrated that Ariane 5 is able to launch in one go 4 Galileo satellite in this time frame without difficulty on the technical side. So as a conclusion, Galileo program is following its incremental path towards the deployment and in-orbit validation with the first launches in summer 2011, and the complete system is now under contract, or will be under contract beginning of next year. Jove and Jove-B have met their mission objectives. They have demonstrated that Europe masters the Galileo technology, in particular for the signal generator and the clocks, and the in-orbit characterization is running well. And we hope now to be able to provide the first services in 2014. Thank you for your attention.
Good afternoon. Let's see if I get there. Oh, thank you. GPS is indeed a revolution, no matter whether your mode is traveling by foot, by car, by bicycle, by train, by boat, by plane, or by spacecraft. There's a GPS receiver that can enhance that mode of operation for you. GPS has pervaded so deeply in our society that even my mother, who will not use a cell phone I gave her and will not touch a computer, understands GPS and uses GPS in her daily life. So GPS never lost again, indeed. But transportation is only the tip of the iceberg of GPS and its applications. Each day there are exciting new applications of GPS that affect all of our daily lives. Slide, please. Precision agriculture has been revolutionized also by GPS. In some certain types of crops, we get a yield 11 times greater with precision agriculture techniques aided by GPS than without. It improves the ability to lay pesticide down, efficiently water, plant seeds, and on and on and on. Dr. Parkinson talked about the timing part of GPS. The small t on his slide actually has a very big impact. The timing portion of GPS influences efficient energy distribution. It's what enables telecom networks to operate efficiently. It even supports operation of the internet. It allows us to do any kind of machine-to-machine interface more efficiently. So GPS is really a cross-cutting technology. And the improvements to GPS, the applications, are built by innovative entrepreneurs all around the world, many of whom are even in this audience. And GPS, however, is a revolution that is still evolving. And in the future, we will have better GPS satellites, better signals, and better applications based on those improvements. Slide, please. A couple of the applications that are topical right now. One is a initiative we have, we call NextGen, which is going to revamp the entire United States air traffic control system. It will now shift to a satellite-based system rather than a radar-based system that is aided by GPS. In the initial demonstration phase done in Alaska, we've seen an improvement of about 30% in terms of efficiency. That's decreased amount of fuel, decreased amount of pollution going in the atmosphere, and we've also seen an increase in safety, less accidents and less near accidents as a result of going to a GPS-aided system. So this $35 billion initiative to redo next generation air traffic control is definitely reliant on GPS and the improvements in the GPS services that are coming down the road. Slide, please. Another system we're working on is called the Intelligent Transportation System, or ITS. Similar to the NextGen system, this is meant to revolutionize the way we do ground traffic management in the United States. Again, reducing pollution, reducing fuel consumption, increasing efficient travel times for everyone. The estimate of the urban traveler in the United States wastes 45 minutes a day in traffic jams. No production occurs there at all. Lots more air pollution, lots of wasting of gasoline. And so by being able to create a network where you can efficiently regulate when the lights are coming on, what paths you should be taking, routing first responders to clear accidents, you're able to increase the efficiency of the entire system. So those are just a couple of examples of places we're headed as a nation to solve the day-to-day problems that face us all. Slide, please. So the current constellation is at its all-time peak in terms of operating efficiency. We have 31 satellites that we call set healthy, which are contributing to navigation solutions today. Our requirement is just 24, so we're considerably above the requirement. In addition to that, we have several satellites that if we needed to, we could set healthy and have them contribute to the service as well. But some of these are significantly older satellites, so we have taken only the 31 best satellites for that solution. But we actually have a large number of satellites above and beyond those that we need. So near term, the risk of a brownout is very low. The concern has been whether the pipeline will support the replacement of satellites before these older satellites wear out. And right now, our estimate is that we will have no problems with brownouts, and I'll show a little bit about that on the next coming slides. We've launched all 8 of the 2RM satellites. 7 of those have been set healthy. 1 is currently in test status. If we needed to, for an emergency, we could set it healthy today, but there are some interference problems on it, so we're continuing to work that. This chart shows that over time we've continued to improve, and while we have set a performance standard, and while most people that are talking about comparing their systems to GPS refer to that performance standard, you can see on this chart that we actually beat that performance standard on a fairly regular basis. And so we have basically several decades of year-to-year continuous process improvement. Slide, please. Okay, so we have a number of different kinds of GPS satellites. GPS is one of those acronyms that's familiar to everybody in the world, but really there's different kinds of GPS. And so to clarify a little bit about what we mean here, the basic GPS system is the older blocks, the 2A, the 2, and the 2R. 2RM, more modern satellites. The 2F series, which is a satellite block that was delayed several years, is now in operation. We have the first satellite up, launched in May. It was set healthy in August. It is now contributing day-to-day to the solutions. The rest of the satellites in that block will be launched starting summer of next year. The last satellite blocks, GPS 3, is ahead of schedule. We call that next generation GPS, a higher power, additional features, the 4th civil signal. All of those are now ahead of schedule. I went to the critical design review. It passed with flying colors, and they're now headed to the production phase. So we're going to have more satellites and more signals. Instead of the classic basic system, which had 1 civil and 1 military signal, you're now going to have several military signals and 4 civil signals on the the completed constellation of satellites. Next slide, please. In addition to that, we're also modernizing the ground network that supports the satellites. Without the ground network in place, you don't get the full utility of the new features that'll be on these satellites. And this system is also on track. We're trying to synchronize the ground control and space segments really for one of the first times since the early days of the program. We've had those out of sync for a while, and we're now trying to get those lined up again. Slide, please. Talked about policy in this morning's plenary, and I just wanted to add that President Barack Obama has signed out a new national space policy, and he singled out position, navigation, and timing because of its importance to the nation and to the world. And he had a few new comments in there. The first two bullets on the slide are really not particularly new. These are things we have been doing already, but he wanted to re-emphasize that we're providing continuous access free of any direct user charges. And it's my belief that having provided GPS free for several decades is what has led to the explosion of innovative applications that we've seen across the world, because the barrier to entry is so low that anybody with an idea can hop on board and provide an application that can improve life for everyone. And so that continues, has been reaffirmed by the current president. In addition, he's encouraged compatibility and interoperability. You heard Dr. Parkinson talk a little bit about that. That was part of the old policy. This policy goes even further. And see in the third bullet, there's actually a specific direction that we can use foreign PNT services as part of our network if we want to. So we are actually engaged with other nations on a very regular basis, and we're looking towards the day when we will be building a system that is using multiple sources of GNSS into our single integrated solution. And so we've gone from discouraging other services and hoping that GPS was the standard to sort of a peaceful side-by-side coexistence, and now towards actively looking to use those services, foreign services, as part of our solution. And then finally, I wanted to touch on the interference issue that Dr. Parkinson talked about. President does recognize this as a serious issue. This is where my expertise lies. I've worked in GPS interference issues for 2 decades. This is what I can help hopefully bring to the table this year for the executive committee that's overseeing these issues. And we do have a number of solutions in progress, from some of the things Dr. Parkinson talked about in terms of greater power, to some hardware solutions that sort of mitigate the effects, to regulatory issues to try to crack down on illegal use of jammers and things like that, to customs inspections, improving the ability to try to stop the jammers from coming in, and then also to being able to detect and locate them, and we've made great strides in that area as well. So we're taking a multi-pronged approach to GPS interference, which is a serious issue, and you can see in the President's policy guidance on increasing resiliency and working with our international partners in that respect. Slide, please. So in summary, GPS is performing the best it ever has. We have the most satellites, we have the best quality of satellites and the best accuracy we've ever done, and the services we have coming down in the future will improve this even further. We have a program that is now on track after several years of hiccups, and in fact the new GPS 3 is ahead of its contracted schedule. These satellites are performing well in tests, and we expect that this will lead to even greater applications based on the GPS system in the future. We're actively engaged with our international partners, both to be compatible, to make sure we don't harm each other, but also to improve each other, to have a synergy where 1 + 1 is greater than 2 by intermixing multiple signals. And also we're proceeding on international solutions to reducing, detecting, mitigating sources of interference. Next slide, please. We produce 2 websites that have additional information. PNT.gov, which will have a copy of this presentation, has a copy of all public presentations that the senior government leaders put out, as well as the policy information, including the full text of the space policy I referenced. That site will also have all of the interface control documents for GPS, the technical specs that the developers in the audience need to build systems to interact with GPS, and any news articles. We'll have funding updates in terms of where Congress is in support for the program, which has been excellent so far. And we also have GPS.gov, which has a lot of applications-related data on those. So if I haven't covered anything in my presentation, please check those sites out for additional information. Thank you.
So, ladies and gentlemen, I would like to start my talk with a very personal reference to the topic of the session, Never Lost Again, because 30 years ago I was completely lost, driving with a motorcycle in an African desert with a magnetic compass, and somehow I got out, but the value of a working navigation system was burned for all times in my memories. So be sure I'm motivated in this area for very personal experience, and being lost in a desert is a very good reference for that. The second point is I would like to apologize that after these lectures in the area of science, of institutional wisdom and politics, I have to go down to the poor hardware manufacturer's point of view. And the hardware manufacturer guys are the guys who have to do the job. If I go to the next slide. What do I have? Very clearly, our challenge in Bremen was, with all the history of Galileo, to do what we call the affordable satellite in terms of price and schedule. Because all these systems need to have, in terms of limited budgets, affordable satellites. And we had to cope with a complete new environment in terms of the customer and contract structure, because this was the first time we have European Union as the end customer and ESA as system prime as procurement agent. But the clear target for us and our partner of Surrey Satellite Technologies was to prove the schedule and the price of affordable satellites, which are also only portions of what was previously projected. The schedule, the price, the cost were all sometimes being called as uncredible. My main message for today's lecture is very short and very simple. Galileo satellites are back on track. If we can go to the next slide. This works. Too fast. The schedule, and you see on this schedule the lighter blue is the actual side. We are fully in track what we have signed, and you see in the picture in Didier's presentation, and I'm not too old for that. We are in line with that. We just passed PDR with some conclusions being ahead of us. We will have 14 satellites, and that's a target, in the year 2014 being ready for launch, and we see no reasons why we will not meet that schedule. Being under contract since January 2010 and having a PDR in this month is not a small challenge. Basically, the success which we have today is not only a success of OHB system, it's also a success of the European suppliers, because 70% of the work is done by European suppliers. What we have shown that we can do that with a tough schedule, we still have to prove that we meet the flight schedule. You see here the launch and the flight configuration of the satellite, which is not revolutionarily new. You see the dispenser for the Soyuz, of course. If you look on the difference to previous concepts is, of course, the modularity. We are very keen to have a high modularity in order to have a safe AIT and especially a short AIT phase. If you compare that with car industry, and probably not all of you know that the typical assembly integration of test of a car, whether it's from Volkswagen or from Ford, is in the area of 23 hours, and they are fighting for each hours. We are not there yet, but unfortunately we are not doing until now millions of satellites. But we have spent a lot of efforts to learn from this automotive AIT and to implement it in the processes for this Galileo program. We have also installed already in Bremen the complete AIT, because we are utilizing the loop integration, and the progress is good in England for the payload integration at Surrey. If you look on the overall global situation, Galileo is not the first system operating in orbit. The coordination, which was already expressed by my colleagues, is also from our point of view a very important point in order to come to an operational system also in the future flawlessly. The coordination especially of the full operating systems which are just building up, and I'm one of the few guys who has served from the equipment side to GPS, to Beidou, or called Compass, and to GLONASS. That is one of the essential tasks we have to see for the next years, and we are supporting fully a cooperative and communicative approach. In terms of the full constellation for Galileo, we have been contracted, like depicted, for 14 satellites. Of course, a complete constellation is a little bit higher. We think that we need at least 27 satellites, operational satellites, plus the in-orbit spares. And this has to be a decision of the next year, very clearly, in order to have a flawless in-orbit spending. In terms of this implementation, it's not only the satellite who is, let's say, something in the budget, but of course the optimization of the launch costs, which might be sometimes more expensive than a satellite, is some of the major tasks we have to do. What is missing from my point of view as an input for this podium in order to end this presentation? I've seen a lot of constellations in my last 20 years. One of them was Iridium, and we see now also Iridium next generation. We also have carefully watched from the European side the GPS, very much flavors and family of satellites. I think it's very important that before you put into space the last satellite of the first generation, you must have a very clear picture of the next generation. Especially the last satellites should be, in the ideal case, already the next generation in order to get that in-orbit verification very soon. Augmentation of the satellites for the next generation in the future will include additional functions. Like our American friends have detailed, analyzed additional functions in their GPS satellites, like ranging, like communication functions. This is an ongoing process. Europe has a big advantage that we have a very broad, highly motivated scientific and technological community who is very daring and willing to implement that. We will support that. Coming back to the major message, and I will stop that, from our point, the Galileo satellite system is on track again. We are very satisfied with the help of our friends in Europe that we are back again to come very soon to an operational constellation. Thank you for your attention.
Well, thank you to our participants. We have about 10 minutes for questions, and there are microphones. And are there any questions? I have one. I don't know who it's aimed at. Is it possible to have too many GNSS satellites in orbit at one time? Anyone have an opinion about that?
Can everyone hear me? Is this microphone working?
Yes, it's working.
I would enjoy that problem.
Well, let's start with the second, and we'll see then if the space is overcrowded. But honestly, today, there are a lot of organizations trying to be the second one, and that's already a challenge to be the second one for being overcrowded.
As a satellite manufacturer, I cannot resist to say a similar point of view on that. But very clearly, we have to look also on the coordination between the different nations. Because you can say we can have a lot of satellites for Galileo, but we need to have, if we have 6 or 7 global satellite systems, we need more coordination. I think we have enough tasks with the current coordination, at least from my point.
Okay, thank you. Something else?
Let me just add, there is an issue of marginal payoff. So there would be a question in my mind as to why, for example, anyone would consider more than 3 or 4 constellations, because at that point, if they are harmonious, if they're all interoperable or interchangeable, the marginal payoff to the user is negligible, and you don't know why they would do it other than perhaps national pride or something like that.
That was more along the lines of what I was thinking. if you have coordination or interoperability among the various systems, maybe something in the 30s is enough in total. Questions? Yes, there's Ed Ashford has a question as usual.
Thank you very much. Just following on from your question, the idea of having too many satellites in any orbit or any series of orbits leads one to question the space debris problem. What do you see as the future means of deorbiting these satellites for the follow-on constellations?
I can speak for what GPS does. What GPS does prior to the demise of a satellite is boost them into a higher orbit out of the way. It still leaves a problem of clutter at that higher orbit, but it's not an operational environment. Frankly, I worry a little bit about it too.
As far as Galileo is concerned, we have the same requirement to put a satellite in a graveyard orbit at the end of this lifetime. At the end of the lifetime,
It's the same thing, so higher up typically than the operational orbit. Another question? Yes, there's one back in the back here.
My question is to Mr. Didier Fèvre. You told us that Galileo is designed to offer two kinds of services, some public for free and some kind of encryption for contracted users. I would like to ask you, is this the same situation as with GPS, the American GPS, in time of military service, and do you think it is a good idea?
almost the same affair. We have different categories of users, so Galileo will deliver an open service as GPS offers today, and for the authorities, European authorities, an encrypted signal, which is more robust, which is quite normal for such a strategic asset. So we follow more or less the line described by the previous speakers.
Okay, thank you. Other questions? Yes, there's one down here. You see where I'm pointing? Right here.
Thank you. My question is with reference of your question, Mr. Moderator. Too many satellites in the orbit, and the problem of space debris is still there. So what if there will be a satellite collision?
I understand the question.
What I'm trying to say that if there are many numbers of satellites, GNSS satellites, right? What if something, such a satellite collision between take place in the time of deorbiting, especially GPS satellites?
A collision.
First of all,
is it not going to create more debris? And is it going to be harmful for other operational satellites?
well, I'm not certain I'm addressing your question, but let me give it a shot. GPS is not deorbited. That would be very, very expensive in terms of propulsion if you study the orbital dynamics. It's just not feasible. So we put them in that higher orbit. GPS and Galileo are actually at slightly different altitudes. They have slightly different periods and slightly different semi-major axes. So in terms of interference between those two constellations, at least, I think it is negligible, and I can't speak for what GLONASS intends to do in the future.
I'd like to add a little bit to that. First of all, the medium Earth orbit is a lot lower level problem than the low Earth orbit, where this is all magnetite. First of all, it's larger in terms of volume. There are less satellites there. It's not used by other than navigation satellites for very many applications. So it's a smaller problem. I still consider it a problem. The other piece is these satellites are in very stable, predictable orbits. So the collision you're talking about is way less likely in medium Earth orbit than it would be for LEO, where you have 20,000 pieces constantly moving around. If it happened, yes, of course. If there's a collision, there's a great chance of increased debris, and that debris would stay in the same approximate orbit and be a problem. But we have a pretty good system in place for identifying what satellites are in what orbit, and as Dr. Parkinson said, right now there's some deconfliction between Galileo and GLONASS just by the altitude. And knowing when things are closing in, and there are procedures in place for somebody moving if they need to. So this is a much smaller problem in MEO than it would be at LEO, which I think is where I'd be much more concerned, and in fact, it's even a safety of life issue, because that's where the International Space Station is. One other thing on debris. One of the reasons we are able to decrease debris is you create a lot of debris on launch. And in the last several decades, we've gotten much better at decreasing the amount of debris we create when we put something in orbit in the first place. And again, most of that debris is in low Earth orbit too. So this is certainly a problem. I think that the nations that are the providers need to continue to talk about it, and that there are forums for that. But I think it's not quite the level of seriousness at MEO that you would see. Even at geosynchronous, I'd be more concerned just because of the number of satellites there.
Thank you. Further questions? Yes, there's one. There's one right. I guess there's one over there. Just 1 second. Yes, Chandra.
Yeah. My question is, I mean, there has been, continuous improvement in the position accuracies over years. And what do you think would be the estimate in terms of position accuracy over the next 10 years, for example, GPS system? And do you think there would be tremendous improvement in the position accuracy because of the multiple systems being operating simultaneously and all being interoperable? Thank you.
Yes, I certainly think you get an improvement in the position and accuracy. I'm not going to quote a number here. I think you do get some marginal returns as you're talking, going from 27 satellites to 30, and then the next jump when you have 2 systems that you're using. So I think you're going to see less and less of an improvement. You're still going to improve with each new satellite that's contributing to the solution. You just won't be improving as much. I also think for those users where high precision is a significant effect, there are other ways of getting that. We look at GPS augmented with other systems, and that's going on today, and I think we're going to see a lot more of that in the future, where GPS is one component of an integrated solution.
Let me add something to that. The real issue in terms of having the extra satellites is not accuracy per se. The real issue is the sky-impaired user. That is a user who, because of buildings, mountains, trees, whatever, does not have a clear vision of the sky. And if you run the calculations, such an impaired user can have very, very limited, just hours of availability in a given day. Densifying the satellites materially and very non-linearly improves that situation. So I don't think that the issue is so much accuracy. Certainly the accuracy is measured by the satellite as the signal in space. And we will probably do somewhat better than that. But we're reaching a point of no returns because it's the local phenomenon, the troposphere and the multipath, that is really driving the error equations now. And as we increasingly get into that, to Tony's point, you're going to use local augmentation that has correlated errors and calibrate that out. That's how farmers get their 1-inch accuracy on a rough field. They do it by, in essence, having a real-time kinematic system that is locally differential.
Get a good signal. And that's something we can improve by having more satellites and having really in the MEO orbit 0 problems of collisions with all other countries, including the GPS system.
Thank you. We have time for one more. Was there someone? We have more than one, so here's one here. Oh.
So you told us about the future GPS systems and the cooperation between the different systems, and that they would probably use the same signal in the same frequency band. Now I'm wondering, the civil use wouldn't conflict with the military application. For example, if the US military wants to jam a foreign GPS signal, but at the same time they would jam their own signal because it's in the same frequency range. Is that a conflict?
Used to be in the U.S. military, so I have a little bit of expertise on this, and that is you still have a need to deny an adversary access to space services if they're using them for purposes hostile to your action. The U.S. approach is to do this on a small localized basis so that you're having as little effect on possible on civilian users, rather than doing it on a satellite basis. So if they were on different frequencies, that makes your problem easier. If your guys are using a frequency that's not being jammed, then yes, it would be more likely to jam that other frequency. When we're talking only wartime environments, only in the area of operations in the war, not those users outside would not be affected. So just like we limit air traffic in a war zone, and we block ships from going to a war zone, and that includes civilian ships and civilian aircraft, there's at least a hypothetical possibility that we might see that in the future. Now, we've actually seen this in real from other nations doing it to the United States. Iraq tried to jam GPS in the Second Gulf War, and fairly ineffective at that. But even that was a small localized area. So I guess the question is, if we have folks on different frequencies, is it more likely that you're going to see jamming in times of military? I would say you're more likely to see that. But again, the law of proportionality would apply that the effects on the civilian population have to be worth the military advantage that you would gain, and would still be a small local area that would be affected.
Let me point out one other thing. I've heard this brought up many times. I think there's a failure to recognize the United States is dependent on the civil signal. It is much more dependent, and it's heading in a direction that is more dependent than Europe is right now with NextGen. So I personally think that the decision to deliberately jam has to be a local one because of the massive disruptions that have occurred. What you may not know is that there was a LORAN that existed in the late lamented war in Vietnam that was not taken out by either side, and the reason was they were both using it. So although LORAN's difficult to jam, it was never jammed. One other fine point is that actually the military signal, although centered on the same frequency, is on the skirts of the band. It is not the new military signal, as well known, is not centered. It is not in the center portion of the band. The current one is, the future one is on the outskirts of that.
Okay, I think unless there's some burning question from someone, we need to, is there a burning question? Maybe there is one burning question, and then we'll call it a day. Go ahead.
Sir, what percentage, if you can identify, is of the capacity is dedicated for military use in these satellites?
Are you talking GPS satellites, the current GPS satellites? When you say percentage, you mean allocated by power? I would say it's roughly half military and half civil, but I don't know what the calculation is. Do you happen to know, Tony?
I don't know the calculation on power. I can tell you in terms of number of users, the civilian users using GPS civil frequencies way outpowers it by at least hundreds of millions. Different civil users. And in fact, as Dr. Parkinson said, even the military is an incredible user of the civil GPS signal. So the military would not want to jam the civil signals for their own purposes because they're using it for all kinds of different applications as well. So I don't know the exact power breakdown on the satellite. I do know that the military also uses the civilian signal. It is a true dual use system.
Okay, we have one last
To reinforce that point, there was a tremendous irony because we had applied a deliberate dither that's no longer even in the hardware in the new satellites, but it was a deliberate messing up with the signal. It was riding it back and forth and making it less accurate. But as soon as the wars started, they turned it back off. Why? Because the military had lots of civil receivers, and they were being affected by the same phenomenon. So I think to the point that was just made, it simply reinforces the notion that if the military, I can't speak for them, but I can speak in terms of probabilities. And it seems to me that if they were going to do anything to disrupt the signal, it would have to be in a very local area because they have so much stake in not doing that. So the real answer from the standpoint of the United States is stop the jamming and put users in place that have capability to ride through it.
Okay. I think we've exceeded our allotted time. I'd like to thank the audience, of course. In particular, I'd like to thank our plenary participants this afternoon.